Hello everyone. Welcome to lecture 18 of Mathematical Modeling and Simulation. In this lecture we are going to look at validation of mathematical model. So this is one of the steps of the process of mathematical modeling, the detailed process. The first step was to think about the real world process, then formulate the model, solve it, and then analyze it. So in the step of analysis, we try to we try to be sure that the model which we have formulated is correct, it is valid for particular kind of situations. So that part is known as validation. So in this lecture, first we'll understand the meaning of verification, what are the methods of verification, and then we'll talk about validation and the methods of validation, and then we'll may look at some aspects of validation. So first is verification. So verification is different from validation. There's a very narrow line between the two words, verification and validation, but still we can understand it. It's the terminology used in most of the times the software models or the models developed by software engineers, the computer programs. So the context is more or less same there also, but it's very frequently used in that language, validation and verification, V and V. So right now we are going to understand what is verification. Verification is like debugging. It is intended to ensure that the model does what is intended to do. It's something like the formula which you have fit in. For example, say you have made a code to add two numbers. So to verify whether your code is running well or not, so what you will do, you'll input two numbers, say 2 and 2, and you'll check your answer. This is coming out to be 4. So that means this is verified. Your algorithm is verified, it's working very well because you have intended the model to work like that, to add two numbers, it's adding two numbers. So that means it's like working fine. That's the verification part. So especially the simulation models, or we have the large computer programs. So there we have these kind of techniques. We verify the code, we make the codes, and then we verify, we test run it over the small examples, over those examples for which we already know the answer. So that's kind of verification of a model. So this is something probably you might have seen even in the course of numerical analysis, where if you formulate or you build the codes for numerical techniques, then suppose you have made a code for solving an ordinary differential equation using Arche method, then first you will verify it for a differential equation whose exact solution is known to you, so that you can verify whether your code is producing the right answer or not. So that's something like verification, model verification. Right, so the modularity and top-down design, these are the few terms used in the context of software engineering. They are part of model verification. So we have various techniques of verification. The first technique is structured walkthrough. When you explain the model to another person, suppose you want to verify your model, so so far you alone were working on your model and now you want to verify it. So the first thing is you will explain the model to somebody else, to another person or group of people, and then while explaining that in detail, you will yourself figure out the problems or the with the current implementation, or the minute details will help you focus on whether the code should be improved or some problem is there. So that means while explaining, so this is something you might have tried even in whenever you're trying to learn something new. So if you start explaining that to other person, sometimes the questions which you had in your mind gets answered by themselves, because that's the human psychology, how it's working. Because when you're trying to explain or convince somebody that your model is right, then you yourself will figure out the reasons why it is not right. So this structured walkthrough is like that, that think your model is not working fine, so you start again, and this is the first thing you can adopt. You can start explaining it to another person, even if the other person is not having any knowledge of that, but still you yourself will be able, the modeler, the person who has developed the model will himself identify the limitations of the problems. So and if you cannot explain it to somebody, so you can prepare documentation for it. You start rearranging the things, or you can say organizing the structure in a document form. Because when we are formulating, most of the time we go unorganized, or maybe we have forgotten some important factor or formula in the code, we forgot some steps, so we start writing it, we start documenting it. So while the documenting, we may figure out, okay, this was a mistake and so on. So that's the verification technique number one. It's kind of revising, it's kind of re-looking at the same thing from a more structured process, in a more structured way. Verification technique 2 is seed independence. So this is something you will not understand right now, because here we'll be talking about the random number generation example, and the random number generation we are going to take up in a subsequent lecture, because that is involved with simulation, the stochastic model part. But you can understand the meaning from here. The seeds used for random number generation in a simulation model should not significantly affect the final conclusion drawn from the model, although there will be variation in the sample points as seeds vary. If a model produces widely varying results for different seed values, it indicates there is something wrong with the model. So this is an important property, seed independence. So whenever we'll be studying the random number generation, so there you can particularly talk about this, that your final answer should be independent of the seed. It is something like your solution of the system in a very long time should be independent of the initial conditions. It's something like, if I give you an example of the population growth model, which we already studied, we know for one population model of this kind, where you have k minus rp. If you remember, this was a model which included a growth factor as well as the decay factor. So the steady state, if you put dp by dt equals to 0, the p was turning out to be k by r. And we know that this kind of model was having an initial condition associated with it. P at 0 is P naught. So that means the steady state solution, the long time solution. Long time means when the things become independent of time. That is K by R. So that's just ratio of these two parameters, K by R. That's independent of P naught. So that means your final answer, your steady state. So what's going to happen in the long run to your system dynamics is purely controlled by some parameters. They're independent of the initial conditions from where you start from, right? So they're independent of P naught. But if your model is having continuous dependence on the initial conditions, so that means there is something wrong with it. You have to modify it. So that's the analogy you can understand here, because here I try to give you an example of deterministic model, but the stochastic case will understand what is this seed and what is this random number generation. So this will understand in further lecture. Another technique which we use for verification is animation. This is also not possible for every kind of model. We cannot visualize, we cannot draw a graphical user interface for every kind of model we formulate. But if it is possible for some models, then we definitely should do that. So it's a verification perspective. Animation provides the information about the internal behavior of the model in a graphical form. It's something like somebody is trying to explain you the situation which is happening, say in a hypothetical movie. Then instead of listening to the person and trying to identify the mistake, you'll prefer to watch the movie and then understand it better, because we understand visually the things better, and we can look at a broader perspective and figure out the mistakes there. So that's also one of the technique to verify your model, that you run its GUI, you run its animation, you try to visualize it through animation or some video, and then try to figure out that everything is working right or not. So there are many techniques of animation. Many people create beautiful animation models for their simulation. They create simulation, we'll understand what is the simulation, and we will also be doing simulations, but we will not be creating always the animation part. So gaming is an, you can say, example of animation. It's basically like a simulation for which you are also having the animation. You're having the visualization with you. So here I'm giving you the example of vehicular traffic simulation. So in this video, you'll see I've run the simulation. and I'll be changing. On the right hand side, you can see I have my controlling parameters here. Inflow, what is the inflow? What is the on-ramp flow? This is the on-ramp side road. If I'll change this on-ramp flow, you will see some changes happening and other factors are also there. So let's just see. This is running at currently these parameters. And now I'm going to change the on-ramp flow. I increased the on-ramp flow and you can see visually that what's happening at the on-ramp, the jam increases. And now again I reduced the on-ramp flow. It will take time to come back to normal because I increased it so much high that it created a disturbance, right? Similarly, you can vary other parameters and see. This should happen if I increase the truck percentage. This should happen if I increase or decrease the inflow. So if all those things are going to give you a reliable answer, so that means your simulation model is working fine. So animation is just a way to visualize the things in a better way. So this is also a common technique of verification. But this is applicable for simulation models. This is not applicable for the theoretical mathematical models. And now we talk about validation. So referring to model validation, so we are trying to figure out firstly an answer to the question, when is a model valid? So referring to model validation, one can state in general that a model can be regarded valid if it is able to provide information on the evolution of a real system sufficiently near to those obtained by experiments. So that means, because see, we have formulated a model for our real phenomena. Some real phenomena is happening, some real system is going evolution, it's changing with respect to space and time. So your model prediction should be sufficiently near to the experiment, because there are two ways of studying anything. First way is to do the experiment on it, and then in our beginning lectures we discussed that experimentation is not always helpful. Like if you want to understand the dynamics of a virus, so you won't be doing the experiment of leaking the virus and probably affecting the whole world. So the experimentation with those viruses is going to be so much expensive, or you can say having bad effects. It's not recommended. So those kind of experiments you would avoid, but you will prefer to formulate or study it theoretically through mathematical modeling. But if you want to validate your model, then the one of the best techniques of validation is matching with the experimental data. So that's what it is telling you, that if the answer of your model is matching sufficiently close. Sufficiently close means it's never going to match exactly, but it can be sufficiently close. Sufficiently close to the obtained by experiments on real system, then definitely we can say the model is valid. So in other words, we can say if the distance means what? It's according to the concept to be properly defined in mathematical terms. So distance means, because there will be numbers, whatever is your output, that depends. If your output is just two numbers, so the distance is just the magnitude of the difference between them. If your output is a vector, so then the distance can be calculated by the norm. You already have studied these vector norms. So it depends upon what is your output. You can figure out the distance between the mathematical distance between your output and the experimental value. So between the simulation and experiment is less than a critical value fixed a priori. It's just like tolerance. It's like tolerance. The difference from the exact value, the error you can say, is, or error tolerance. So we fix error tolerance in our codes as, say, this is 10 raised to power minus 5, that if your error is going to be less than that, only then we are going to accept that the code is working fine, or the approximation or the model is working fine. Then the model can be regarded valid, otherwise revisions and improvements are necessary. So that's what the meaning of validation is. And now let's explore this validation further. For most models, there are three separate aspects which should be considered during model validation. The first is assumptions. Okay, now we want to validate the model. So it's not like we just need to validate the answer. We also need to look at the basic assumptions which we formulated in the beginning for our model. For example, if you want to study the effect of weather on a certain phenomena. say on the virus outbreak, so say of the viral, which is very much prominent in the rainy season. So if you want to build a model for that, understanding the dynamics of that viral outbreak, so if your model does not incorporate the factor of weather there, it does not assume explicit dependency on weather there, so that means your model assumption is wrong. So that's just an example to explain you that whatever be your initial assumptions should be in line with the your purpose of modeling. You want to study the effect of weather, so your assumption should not be ignoring the weather or any factor directly or indirectly. So first thing in model validation, we look at, okay, whether our assumptions are correct or appropriate or not. And then we look at the input parameter values and the distributions. So it's the same thing when you're running a code. If you're getting a wrong answer, so you just start looking at the parameter values. Okay, have I put any numerical value wrong? Suppose a particular alpha was supposed to be 0.05, have I substituted it 0.5? So that's something like parameter validation, that the values which you have given to your parameters in the model, maybe you are taking those values from literature, maybe you are taking those values from some experiment, are those correct or not? So in this step, we look at in detail the parameter values and the reasons why it should have this much value, and distributions in case of the statistics or the probabilities. And then we also look at the output values and conclusions. So basically your model gets validated throughout, starting from assumptions, then the input parameters, and then the output values. And how to do the validation? So there are three steps. Just like here, now I discussed three techniques of model verification. So for model validation also we have these three techniques: expert intuition, real system measurements, and theoretical analysis. So firstly, we are going to talk about expert intuition. So it's similar to the structured walkthrough. It's similar to the verification technique number one, structured walkthrough, which I gave you. There we take the where we do not take advice from anybody, but in structured walkthrough, in the verification of model, we just explain the model to somebody, and we do not care or we do not expect any feedback from the listener. But in expert intuition, we somehow are getting our model tested by an expert. Essentially, using expert intuition is similar to use of the one-step analysis during model verification. Here, however, the examination of the model should ideally be led by someone other than the modeler. So it's shown to an external expert rather than with respect to the model. This might be the system designer, the service engineer, or the marketing staff, depending upon the stage of the system within its life cycle. So that really depends upon model to model, that to which expert you should be taking in guidance from, or seeking validation from. But this is somewhere recommended as one of the things. Like the very first time, something like publishing papers in journals. You have given a new model, so you are taking the advantage, or you can taking the advice or suggestions from the experts in that area. So they'll give feedback on your work, and they will intuitively predict or say that this model is appearing fine, this model is looking fine. So that's the meaning of expert intuition. Validation technique 2 is real system measurement. This is something I've just explained in the beginning, and that's the meaning of validation is that you compare with the real data. You get the model output and then you compare with the real data. So that's the most reliable and preferred way to validate a model. In practice, this is often infeasible because either the real system does not exist. For example, you are building a model for, say, you're studying astronomy, you're studying astrophysics and making a model for solar system or something like that. Let's not go into the details. So something like that for which it's not possible to conduct the experiment. So there where you will validate the data from, where you will get the data from. So in some cases the measurements are not also accurate, the data is not very much accurately available. You want to make a model for a particular city, a traffic flow model for a particular city, but you do not have any data available. So how you will validate? or in some cases the experimentation is expensive or dangerous. So then we do not have any way of validation through the real data. So that's the only limitation of this validation technique, that if the data is not available, then we cannot just validate it. And then we have, in the same technique, on what basis we can compare with the real data. We can compare with other models. So that's also a very frequent technique used, that whenever you formulate a new model, we first compare it with the existing models. That the earlier model was giving this prediction, this model is giving this prediction. So if the predictions are like very much different, so chances are your model is not working fine, because if that is, the earlier model is a established model that is validated already, but your model is giving very opposite answer than that model, so eventually it will be proven that your model is wrong. So that's the benefit of comparing with other empirical models, that you can get an idea whether your model is going to the similar line. See, quantitatively it can differ. That model is giving you 3.5, your model is giving the value 3.55. It's more precise, it can be more quantitatively right. But the previous model was giving value 3, your model is giving value 120, and that previous model is already validated. So that's a huge difference. So depend upon model to model. So that means comparison with other models can give you a very good idea of your model. Comparison with analytical models. So it's the same thing, like for your model, say analytical solution is not achievable. We have seen various models for which we cannot derive the exact solution, so we solve them numerically. But what you can do, you can compare them with those models which can be solved analytically and get your answers compared. Then we can do comparison with hand calculations or reprogrammed versions of model components. This one is very frequently used in, again, coding or programming, that your program seems to be valid, or you want to declare this is going fine. So you start working on the smaller versions. It's the similar thing I gave you an example in the beginning for verification, that first you will try it on a very simple example. If it works fine for every small example, that means the chances are it's going to work fine for even the bigger example. So that's the meaning of compare with the reprogrammed versions. Examination of reasonableness and accuracy, that is comparison with understanding. So this is something coming from your intuition. So here also we can have the example of say there is a famous model of traffic flow. It's a second order model. We in this course just studied first order macroscopic model, that was LWR. So this was the first second order model. Someone just went from just including the law of conservation of mass, we also included law of conservation of momentum there. And his model was giving inaccurate answer, because according to that model, the information was coming from both the sides. While we know that in traffic, the information is just coming from one side. You are going to drive your car by looking in the front, not by looking at the back. So the information which is telling you to maintain your driving behavior is coming from the front. So his model was telling that information is coming from both the sides. So that means the physical intuition, the physical or the common sense, or you can say of the parameters or of the conclusions, tried to uh, tell us that that model was wrong. So it's something like the intuitively that model was wrong. It was not matching with what should happen according to the physics of the model. So this is examination of reasonableness and accuracy in comparison with the understanding. And then examination of appropriateness and detail. So that's also something which is depending upon the model to model, how much detail you want to do examination, if that is included or not. And then there's validation technique 3, that's theoretical results or analysis. In the case of models, it is sometimes possible to use a more abstract representation of the system to provide a crude validation of the model. So it's similar to that a particular model which you have solved numerically. Say you are not satisfied or you want to validate that whether this numerical technique is giving right answer or not. So what you will do, you will simplify your model to an extent where you can solve it exactly or analytically. And in that version, that simplified version of the model, that you can compare numerically and analytically. So that will also give you a fair idea that the line on which you are deriving the numerical technique or formulating the numerical model is right or not. So that means theoretically you need to get some idea for it. It's not always possible for the complex model, but if not solving exactly, but we can always do some sort of theoretical analysis to match with the experimental or the model results. So this also is coming examples coming from the operational analysis, that in particular if the results of operational analysis based on operational law coincide with the model output, then we can take it as an evidence that model is behaving correctly, right? And while the failure of operational laws would suggest that further investigation is needed. So that's all about the validation part. In our next lecture, we are going to look at another class of models, epidemiological models.